Good morning. In today's lecture, we'll completely switch gears from the course of discussion we had so far. So far, we studied the classes of organic compounds, the structure, and their reactivity. And today, and in the next couple of lectures, we will see how do we actually prove that the structure we propose and write on the paper for a certain compound is the actual structure of that compound. This task can be performed through either chemical means, where we expose a compound to a series of reagents, which then confirm that it has or does not have certain functional groups. But the problem with such characterization is that it's destructive, so that instead we lose our sample, and that is the problem, especially if our sample is very valuable. Therefore, the physical characterization methods are preferred to the chemical ones, especially if they're non-destructive methods that use very little sample. Okay? Now, in terms of information we're looking for when we want to characterize an organic compound, we would look ideally for three pieces of information. The first one would be size or mass of the molecule. And this information, as we'll see a little bit later on, comes from the technique known as mass spectrometry. Especially in organic chemistry, we're also looking for functional groups. And this information will be provided to us by IR spectroscopy. Finally, we ideally want to establish the position of each carbon and hydrogen atom in the molecule. In other words, we want to discover what the carbon skeleton looks like. And this information comes from the most powerful spectroscopic technique we'll talk about not in this, but in the next one and the lecture after that. And that is known as nuclear magnetic resonance, or NMR spectroscopy. Okay? And so, as you can see from here, this is there is not one technique which gives us all the answers. We need to combine techniques which operate on very different physical principles and give us very different information. So we need to create a composite of that information to get to the final structure. And so the first technique we'll start talking about today will be mass spectrometry. And as its name implies, this technique provides us with the molecular mass of a compound. And this already is a very significant piece of information because it allows us to distinguish between different possibilities for gross molecular structure. So if we start with combustion analysis, which is a chemical technique, and it's not a very modern technique since it typically consumes about 10 milligrams of your sample, which is quite a bit, and destroys it. So if we start with combustion analysis, we will get X moles of CO2 and Y moles of H2O. And this will tell us, so Y1/2 moles of H2O. And this will tell us what the ratio of hydrogen and carbon is in that molecule. However, this will not allow us to distinguish between compound with the formula CXHY or compound with formula C2XH2Y, or compound with this formula. Okay? And to figure that out, we would need to know what the mass is. And mass would allow us to tell the difference between these three compounds, because one obviously will weigh 2 times as much as the other, and the other one will weigh 3 times. And so the technique that allows us to do this is mass spectrometry, and the instrument is mass spectrometer. And, we're going to see now a simplified representation of a mass spectrometer. A mass spectrometer is basically a curved tube, where at the beginning of this tube we have our sample, and next to our sample is the electron beam. After the sample is vaporized, this electron beam shoots electrons onto it, which then ionize the sample. And then once we get these ions, they are moving towards the accelerator plate, which accelerates them simply by using electric field. Okay? The ionization comes from these high-energy electrons, which shoot at the sample, and then they hit it with very high energy of about 70 electron volts, so hard that they actually bump out another electron out of the sample and give us a molecular ion, which is a radical. It has an unpaired electron. And now this ion is charged, and negatively charged accelerator plate is able to attract it and speed it up. Okay? And so such attracted ion then enters a magnet. And magnet, again, is a curved assembly which looks sort of like this. And this magnet deflects the path of our electron. And deflects it regarding, depending on the M to Z ratio. So the ratio of the ion's mass and its relative charge. Okay, and so once deflected, this ion will now take a different path and eventually hit the detector. However, only an ion of certain mass, which can be adjusted, will do this just right and deflects only to the point that curves enough to actually hit the detector. If an ion is too heavy, then the magnetic field will deflect it too little and it will hit this magnet and that therefore be removed. If the ion is too light, it will be deflected too much and again it will hit the magnet. And so at any given time, we will get only one class of ions far enough to actually hit the detector, and by varying these parameters of the mass spectrometer, we'll slowly get our mass spectrum, which will give us a peak for each individual mass in the center. Okay, because of the phenomenon that produces the ion, that is electron impact. This is known as electron impact, or EI ionization spectroscopy. And this is one of the most common molecular techniques in mass spectrometry. Now there are several parameters of a mass spectrum which are of interest to us. The first and the most important one is the highest peak, M+. And this is the mass of our molecule. And this is the peak at the highest M over Z value. This ion is also known as molecular ion. Clearly this is an important parameter because it tells us the molecular weight of our compound. If we draw out the mass spectrum, then this x-axis would be M over Z value in Daltons, and we would see a number of peaks at different MZ values. The one at the highest MZ value is typically our molecular ion. However, molecular ion does not necessarily have to be the most intense peak. Okay, in this case, it's not. So this peak is the most intense one, and this one is known as the highest base peak, so the tallest peak. Just as a bookkeeping method, this peak is often labeled as 100%, and all other peaks are expressed in percentages of the value of base peaks. So this would be maybe, I don't know, 45, and so on. Okay? Now, the question is, if you have a pure sample, we should get only one peak for the mass of that sample. However, things don't turn out to be that simple, as you see already in this mass spectrum, because we have multiple other peaks. And these peaks are known as fragment ions. And they come from the fact that once we knock out an electron from a molecule, that molecule is no longer necessarily stable, and oftentimes it fragments, it breaks apart even further. And that we detect these little ions that come from the fragmentation of the central ion. Now that is sometimes a problem because our molecular ion is so weak that it's very hard to observe. But oftentimes it can actually help us because the certain classes of compounds have certain fragmentation patterns that allow us to identify them in mass spec. We're not going to get too deeply into fragmentation, but to illustrate just one example of what I mean here, if we take just a simple molecule of ethane and expose it to high energy electron, we will get the molecular ion. But this molecular ion can now break up into methyl radical and methyl cation. The radical is uncharged, but the cation is not. And so the cation will be accelerated towards the magnet, and we will detect, in addition to this, we will also detect this cation. Okay? Now, clearly the most important piece of information that comes out of the mass spectrum is the mass of our molecule, and that is already a big help. But there's other pieces of information that we can extract from mass spectrum if we analyze it carefully. Okay? So if we the first thing that we can do is see whether we have nitrogens or not in our molecule. This is not very straightforward, but if you think about it, most organic compounds have even mass. If you look at diethyl ether, and this is 15 for methyl group, 14 for CH2 group, 16 for oxygen, 14, 15, and overall this mass is even number. The same thing would apply if we remove this oxygen and just have butane. That would still have an even molecular mass. However, since nitrogen is trivalent, it will attach 3 alkyl groups. And since each alkyl group is 1 hydrogen short of an alkane, it must have an odd mass. And so here we will have 15, 14, 14, 15, 14, 15, and 14 for nitrogen. And so a nitrogen-containing compound, if it has only 1 nitrogen, will have an odd molecular mass. Now, if we have 2 nitrogens, again, we will have even molecular mass. But if we have 1 nitrogen, we'll be able to detect this in the mass spectrum. So that's an interesting and important piece of information that sometimes would be difficult to get through other methods. Another piece of information that we can get is whether we have bromines, chlorines, or not in our molecule. This is something completely new. But if you think about, or if you look up the bromine and chlorine in Wikipedia or some other reference, you'll see that the bromine is actually a 1-to-1 mixture of 2 isotopes, bromine 679 and bromine 81. And the chlorine is about 3-to-1 mixture of chlorine 35 versus chlorine 37. Okay? Now, what does this mean? This means that in a spectrum of a compound with bromine, we will get 2 molecular ion peaks. There will be 1 peak which corresponds to a molecule which has bromine at 79, and so this will be M+. But then 2 mass units away, we will have M plus 2 plus. Okay? And these peaks will be 1-to-1 because bromine isotope ratio is 1-to-1. In the case of compounds with chlorine, we will have the same distribution. This will be M plus, and this will be M plus 2. This will come from chlorine 37. But the ratio will be 3-to-1 because the corresponding isotopes have that ratio. This is actually an extremely important piece of information because it's very identified chlorine and bromine in organic compounds is relatively difficult by IR spectroscopy or even by NMR spectroscopy, as we'll see later, because they don't have any hydrogens directly attached. But in mass spectrum, this is super easy and it's very diagnostic. And so this is probably one of the most important pieces of information we can get out of the mass spectrum, presence of bromine and chlorine ions. So if you have doubled up molecular ion peak, that will probably indicate that you have either bromine or chlorine. If you look at the intensities of these 2 peaks, if they're roughly equal, that will be bromine. If one is about 3 times bigger, this will be chlorine. And again, this is something that you can notice without really doing too much measurement. If they're roughly equal, that's probably bromine. Okay? Now, mass spectrometry, we have to say, is a destructive technique because if you think about the mechanism it operates through, mass spectrometry ionizes the sample, at which point it's already destructed, and sometimes it even fragments, so our compound is clearly gone after it goes through mass spectrum. But it's a very sensitive technique. This mass spectra can routinely be run with less than a milligram of compound, so very small amount. And so even though it's destructive, it uses so little sample and it provides a lot of information that people still use it as a modern technique quite a bit. Okay? However, just like any other technique, it has its limitations, because if you look at a molecule like this will have a mass of 86 grams per mole. And if you look at this cyclopentanol, this will also have a mass of 86 grams per mole. Okay, so mass spectrometry, in principle, could distinguish them, but it's not going to be easy. Okay. However, these compounds seem quite different from each other, and the main difference with them is that they're functional groups. So having a technique which would allow us to identify functional groups would be extremely useful as a complement to mass spectrometry. And in the next subtopic, we will see a little bit about electromagnetic radiation, and then the topics following that, we will see the technique IR spectrometry, which is actually used to identify functions.